Hi, and thanks for joining me. My name is Doug Wagner. I'm an instructor at the University of Regina in the Faculty of Engineering and Applied Science. And this is second in a series of videos dealing with fault calculations in electrical systems. And in this video, we're going to look at sequence networks. Part 1, we looked at symmetrical components, a way of us describing our three-phase system and breaking it down so that we had a mathematically simpler system to deal with when we had unbalanced faults. Now we're going to look at the circuits that we put together in order to get those symmetrical values and then in turn use them to calculate what our actual fault currents are. So our objective is to develop our positive, negative, and zero sequence representations for systems under study, and then we'll look at how we would apply those. So we're going to consider a system here, so I'm going to switch over to that. And in this system, this is a rather fanciful electrical system. What we have is coming from our reference, or what would be essentially our ground. We have a source, a generator, that's operating with a line voltage of 25 kV. It has some impedance. Now here I'm just showing it as a straight J 0.5 ohms. When we deal with generators, we actually find that their impedance can vary depending on whether we're looking at the positive, negative, or zero sequence components that we're dealing. And the symbol over here is showing us that this is a Y generator and it's solidly grounded. Now I'm going to a bus, again just a point for reference and connection. Then I have here in the European form a transformer. Again, it seems a little odd. It's a 25,000 volt to 25,000 volt three-phase transformer, and I'm showing it as having an impedance of 0.3 ohms. What I haven't shown, and becomes very important to me, is what are the connections like on this transformer. They can actually be in a number of different forms. Let's just take a quick look at that. My transformers can be connected where I have on the secondary a Y connection, and on the primary, or primary and secondary, a Y connection. So I can have YY with no grounding connection on either side. I can ground either side, one side or the other, or I could ground both. Probably the most common form of transformer we see in electrical systems is where I have a delta connection on the primary side and I have a Y connection on the secondary side. And I can also see transformers where I have a delta and a delta connection. Now, the significance of these types of connections comes into play when we look at our zero sequence network. There's two things that are challenging for us when we're dealing with our sequence networks. The first is finding the actual Thevenin impedance of a complex network from our fault point looking back. And the second is making sure we get all of our sequence networks, particularly our zero sequence network, correct. So let's go back and look at our system, and then I have my transformer. Right now I'm going to leave this blank in terms of showing what we have. And then I have a bus here. And this bus is going to be faulted, and my faulted bus, this represents a load, and this is a transmission line that has an impedance of J2 ohms. It's very common when we're dealing with finding fault currents that we neglect the resistance in our system because our inductance is always going to dominate, and we can consider it just as a purely reactive network. Makes some of our calculations a little easier. So now I want to talk about what type of faults I typically see. So in my system, I can see the following faults, and we'll deal with this either in the review session or in the third video. But I can see a three-phase short, or what I would call a three-phase fault. All three phases are shorted together. They may either be directly shorted or faulted through some sort of an impedance, some value of impedance. I can have a single phase to ground fault, where that's one phase is tied to ground. I can have two lines shorted together or faulted through an impedance, and I can have two lines that are faulted to ground as well. And then finally, although we're not going to deal with them today or in these videos, we can have open circuit faults. Now, of this list, the most common fault that we will see is actually in our utilities. We will see single phase to ground faults dominate. They dominate because largely through weather events, we either get lightning flashovers on a single phase or we get tree contacts. In utilities will also see double line or line to line faults that can be caused quite easily by birds, and a double line to ground fault can occur when we have a protective conductor known as a shield wire, which is at ground potential falling across two phases. In industrial applications, we quite often pretty much only see three-phase faults, although we do also see single-phase to ground faults. In the previous video, we developed symmetrical components as a way of expressing the positive, negative, and zero sequence components of any current or voltage. Now what we're going to do is we're going to look at the sequence impedance circuits that we have when we're considering these positive, negative, and zero sequence components. So here I have three representations, or three circuits, which represent that model that we were just looking at. So here I have a voltage source called VA1. I have an impedance ZA1. This represents the Thevenin equivalent impedance that I'm going to see for my positive sequence network. And I have a voltage source. So this is my positive sequence network. Here I have another network which represents, again, you'll notice there's no voltage source, and there's an impedance ZA2. So this is my negative sequence. And finally here I have a ZA0. ZA0 and no voltage source represents my zero sequence. Now, not all of these networks apply to all faults. They all exist for our circuits, and we're going to see that what's involved for us is how do we connect these networks together when we're actually analyzing a fault. How we connect them, and then how we calculate our resulting currents. So here, the resulting current I'm interested in is IA1. Here be IA2, and here IA0. Again, I'm finding the sequence component of the A value, and from that I can find my IB0 and my IC0. They're easy, they're all going to be the same value. And IA2 is going to be shifted, or IB2 will be shifted in phase with respect to IA2, and so on. So now the question is, how do we connect these networks for various faults? So let's look at that. I'm going to look at first my three-phase fault. So with the three-phase fault, only IA1 is considered. So if I have a solid fault in my three-phase system, my sequence network for finding my fault current would be this. Then, if I have VA1, IA1, and IA1 is going to be equal to VA1 over ZA1, IA2 is going to be equal to 0, and IA0 is going to be equal to 0. So now, with this expression, I can find IA1, and that in turn will allow me, with the material we covered in the video, to find IA, IB, and IC during the fault. And again, this is why we want to do this. We want to be able to find those fault values. Now let's look at our single line to ground fault, abbreviated as SLG. So in my single line to ground fault, what I'm going to see, and we're not going through the derivation here, but I'm actually going to see that I'm going to have my VA1, my positive sequence, ZA1. Then I'm going to flow through. So here I have IA1, here I have ZA2, and I have IA2, and finally I have ZA0 and I have IA0. And here is my ZF. We'll say it's equal to 0 ohms. Now what do we see here? Well, we see IA1 is going to be equal to IA2 is going to be equal to IA0. So in this case, we have all three currents flowing, and we have our faulted current. And from that, using the components we looked at in video 1, we can actually find our IA, IB, and IC values. Now, we'll see it becomes interesting. In some cases, ZA0 is going to be substantially different than ZA1 and ZA2. In 99% of the cases, ZA1 is equal to ZA2. It only varies with some generators, but for all transformers and transmission lines, it's going to be equal. Our next condition we want to look at is our line-to-line fault. And in this case, what I have VA1, IA, then connected in parallel. Looks a little funny as I draw this. I have IA2 in this case, and ZA2. So what we see in this case is that IA1 is equal to minus IA2, and can be found in this case IA1 is going to be equal to VA1 over ZA1 plus ZA2. When we do this calculation, and then IA2 is going to be equal to minus IA1. At first glance you might say, well, then does that mean on a line-to-line fault that our current is half? Well, remember, our sequence current here is going to come out to be a different value, but when we plug these values in, because we have now a non-zero IA1 and non-zero IA2, our actual currents in the lines are going to be significant. So we have to carry through and find our IA, IB, IC. Now, the last one that I look at, just for reference, a line-to-line to ground fault, is going to look very similar, where I have VA1, ZA1. Now, what I see is ZA2 in parallel with my zero sequence circuit. So I actually have to find, if I was to actually go through and solve this problem, I have to apply current division between the negative and zero sequence branches to actually find out what my currents are in each one of these branches to find IA0 and IA2. So essentially we have these two in parallel, then in essentially that impedance is almost in series with my positive sequence. So those are my sequence networks. Now let's look at how we actually get these values. So when I'm looking, and I always start from where my fault is, I want to essentially find the Thevenin equivalent impedance looking back. So I have an ideal voltage source here, its associated impedance. I have the series impedance of my transformer and my transmission line. So it's a very simple series circuit in the way I've drawn this. So in this particular case, my positive sequence in this would be the sum of these values, 0.5, 0.3, and 2 would be J2.8 ohms. And that's also going to be equal to ZA2. Seems easy, seems straightforward. Now we'll talk about the transformer. When I introduce my system components, my generators, transformers, and transmission lines and conductors, I have to be aware of how they behave when I'm looking at my zero sequence, or essentially the impedance with respect to ground. So this is out of the Chapman textbook, but this is a good reference. We can see that our transformer connections become critical to us in terms of how we're connected. So here I have a series of transformer connections. In this case I have a YY transformer with one side of it grounded. And if we look here, my equivalent zero sequence circuit for the transformer alone is an open circuit. On the P terminal here, I do see the impedance, but it connects nowhere. Another way of thinking of this is there's nowhere for ground current to flow. In this next connection, which is a Y grounded transformer, you'll notice that in the zero sequence, I have a connection straight through in series with, from P to Q, with the Z0 or the Z of the transformer. The next one, I apologize for my fingers being in the way, which is again a very common configuration we see, is where I have a Y grounded transformer and I have a delta connection on the other side. So you'll see coming from the delta side coming in, I have no path for ground current to flow. Coming in from the Y grounded side, I have a connection from P through this connection to ground to my reference, or to my neutral, to ground essentially. So this is important when we're looking at our circuits. Here I have an ungrounded delta Y, you'll notice I have no connection. And finally, when I have a delta to delta transformer, I have no connection from P to Q. They're both broken here. But actually there is the potential for ground current, if I get it into the transformer, to flow. That can be significant if we have something known as third order harmonics in our transformers. It's beyond what we're talking about right now. So let's go back and look at our schematic or single line diagram and put some values on here, how we would come up with our various impedances. So the one that's of interest to me I've already found the positive and negative sequence. Now on this transformer, I'm going to make it Y delta with a ground here. So now if I was to draw the Thevenin equivalent circuit that I have, I'll start off here with my reference in the zero sequence. So I would have J 0.5 ohms. I'm showing them all being the same value off the generator. And then I have no connection. But what I have now is I have a direct connection from my transformer, J 0.3 ohms. Then I have my transmission line of J 2 ohms to my fault point. So in this case, Z0 would be equal to J 2.3 ohms. So if, for instance, I was solving for a single line to ground fault, all three of my sequence networks are in series, I would have J 2.8 ohms in series with J 2.8 ohms in series with J 2.3 ohms. A couple of things that are worth noting. When I have a fault, or if I have some impedance in my neutral circuit, then when I consider my sequence networks, it's Z0 plus 3 times ZF, or Z0 plus 3 times Zn in my calculations. So I'll just again, I'm giving a very, very quick overview of this, but this should be useful for us as we go through our work in this. So what we've done is we've been able to look at how we would build up our circuits. Now, I've done this very briefly, but this should give us enough tools now that we can go on to our next item. I hope that there's a part 3 video, or if not, we'll do this in person in a seminar review. Then we'll go through and we'll put it all together and do some actual fault calculations. Thanks for watching.